Everything is okay.
And okay. So hello. This is the fourth lecture of the series of disguised toric dynamical systems. So let's just let's see a couple of slides to recap what we saw last week, just to get again in the context.
Excuse me, Miruna. May you
Yes.
please accept it? The meeting is being recorded. Just press OK on your screen. On your screen.
I'm sorry.
Okay. Please continue. Please continue. Continue.
Is it recording? Is it?
Yeah. Recording is set now. Okay. Continue.
Okay. I didn't press any OK yet, so if I have to, then. Now. Okay.
At the top. At the top. At the top of your screen, just see.
It didn't appear anymore. For me. Usually it appears.
Yeah, it's on our side, not on your side. Please continue. Sorry for the confusion.
No problem. Sorry, I don't see any. Okay, I'm sharing the screen now. Yeah.
Okay, please share the file and continue.
Yes. So now I think you can see the. Yes. So last week we saw this terminology of toric dynamical systems and their advantages from the application side and from the algebraic side. So both nice dynamics, local stability, sometimes in some cases proven globally stable, and in some other settings, algebraic. From the point of view of algebra, we have these equations that are polynomial equations that one can where one can plug in the parameters and then check if indeed the system is enjoying these nice properties, if the system is indeed toric. And we saw how to get those, and we used tools from algebra, commutative algebra, computational, elimination theory, and so on. And as we saw last week on an example, we have this recipe to get the toric locus. Okay, and you use matrix tree theorem. We use the ideals and so on. But the bad news there was that, as you noticed, the toric locus is usually a set of Lebesgue measure 0 in the parameter space. There was a set of codimension 1 in the previous example. So it's usually difficult to find in the parameter space such nice systems. That's the problem. That's the motivation of this work, because we notice that picking such a system is, since they are rare, it might be difficult in practice. So here comes our contribution with Laura Brustenga, Imon Cuzi, Gheorghe Crăciun, and myself. We actually extend the toric locus to the so-called disguised toric locus. And what is very important is that the disguised toric locus preserves or has the same nice properties as the toric locus. So in the sense that the dynamical systems that come from the disguised toric locus will be again, as before, as I mentioned, locally stable and very nice on the long term. But the advantage is that now the disguise, so I will make this precise soon with the concrete examples, but just to give the main idea, the disguised toric locus is of positive Lebesgue measure. So this is the benefit. Now we find many more with this algorithm that we have, many more nice systems. coming from the network that we start with. We'll see that actually by using other networks, but we'll see now. We start with a network, but as tools, we use some other network. Okay, so what we leverage is the notion of dynamical equivalence introduced by Crăciun, Jean, and you. And at the end, as I mentioned also last week, there are cases where we know that there exist globally stable systems that are not toric. So we knew this. There is in the literature this thing, but the question is now if we extended the toric locus with a disguised toric, did we cover all globally stable systems? So we were wondering if now with extending to the disguised toric locus, there are no more globally stable systems that are not disguised toric. And we'll see the answer to this in a bit. So this is the plan for today. To start by recapping a bit what we saw last week. So the moduli space, it was called in this way in the paper by Crăciun, Dickenstein, Schwer, Sturfes. They showed that the moduli space associated to any toric dynamical system is a toric variety after a change of coordinates. And we remember from last time this example with the complete directed graph on 3 nodes, 3 vertices, and the hypersurface where these parameters lie, the parameters that give rise to toric dynamical systems. So essentially, the toric locus is this hypersurface. And just remember how it was this change of variables and with the spanning trees, or more generally, the matrix 3 theorem gives us this, and you can read this more in the paper by the 4 authors I mentioned before. Okay, and as I said, it has Lebesgue measures here. Just to recap the last example we saw on Friday. But actually, this theory of Lebesgue measure 0, what I'm saying here, is a more general phenomenon that can be precisely explained using an invariant of the network that you start with, that is called the deficiency of the network. What is the deficiency first? So if you have a graph that we say Euclidean embedded graph, take the reactions of the edges and see the space spanned by those edges. That is our stoichiometric subspace S. We encountered it already on Friday and before. And denote by S the dimension of this space, small s here. Moreover, look at the graph and see how many connected components it has. And we denote this by L, here. In chemical reaction network theory, sometimes connected components, or usually actually, usually connected components are called linkage classes. So a connected component is called a linkage class. You might see this in the literature. So it's just another terminology for connected component. Denote by L the number of such connected components, and by M the number of vertices. And now the deficiency is just this non-negative number that it's an integer, and it's the difference between the vertices. And so take number of vertices minus S minus L minus the previous notations here. In our reaction that we kept looking at, this triangle on a line, we call it. So here we have 3 vertices. We have 1 connected component. So we have M equals 3. We have L equals 1 connected component, and we have the stoichiometric compatibility. Okay, the stoichiometric subspace has dimension 1 because the edges of the graph span just a 1-dimensional subspace. So here we have that we have that the deficiency is 1 for this network. Why do we care about this deficiency? So besides the fact there are some other theorems that directly infer some results from just by looking at the deficiency, and like deficiency 0 theorem and so on. I don't mention too much now. Our theorem from last week also included, so I mean, Crăciun, Dicăstănescu, and Sturmfels not only proves that it's a toric variety, the moduli space, so, okay, the toric locus, but actually they also prove that if the graph is weakly reversible, then, so this is a combinatorial property on the graph. Every directed edge is a part of a directed cycle. So if we have this, then the deficiency of the network is the codimension of this variety. So what I was saying with the set of Lebesgue measure 0, it's actually made precise by this theorem. In general, we have this, so in applications, many times deficiency is positive, so it happens to be, the toric locus happens to be of Lebesgue measure 0 in the space, in the parameter space. As I said, this is making sense now because we had this hypersurface here and for this network, and indeed we computed the deficiency is 1 in the last slide here for this example. And with this example, soon we will start looking what we can do to improve the situation, to find, because for now what we know, using all this theory by Crăciun and Dicăstănescu and Sturmfels, is that if the parameters of your network, so the Kij's that decorate the edges from here in the mass action system, are lying, if the parameters Kij lie on the hypersurface, we know that it is we have complex balancing. So nice dynamics I was mentioning by Horn and Jackson, and so we don't know anything about what happens outside this hypersurface for now. We just know what happens on here. So here will come our improvement, because we will find some more parameters outside this hypersurface that also give rise to the same nice dynamics. And we will look at several classes of reaction networks in this talk, and also we'll see a general procedure, a systematic way to extend this locus, so that hopefully maybe some of the participants here, we can together or separately find other interesting classes, because since it was very difficult computationally to extend the toric locus in some examples, we didn't, so we just treated some networks or classes of networks. So there's still much more to discover here, I would say. Now, I just, for the sake of having the notations, I recall what is an Euclidean embedded graph, or E-graph, because I want to have the notations now clear. So a Euclidean embedded graph, we also call it E-graph, is a directed graph. What we have been seeing until now, VE, so V the vertices, E edges. Let us suppose that there are no self-loops, and there is at most one edge between a pair of ordered vertices. Sometimes we use this notation for an edge of the graph. We say that we have the source and the target and an arrow in between, and we say it belongs to E, to the set of edges. And we need now several definitions, just they're not complicated, but they're crucial now for understanding the disguised toric locus. So the first definition is that if you are given a graph, an E-graph, let us denote by f index gk this function that we already encountered from when we created the mass action ODE system. So here this is a vectorial notation, and you see we have the graph decorated with the rate constants with the k's. We have the vertices of the graph and take these differences, target minus source, and the monomial x to the power y here that makes it exactly the shape we had we saw on Friday for creating the mass action system. And okay, recall that these parameters Kij are called rate constants in the literature of chemical reaction networks. We see them as parameters. And now the main, so very important definition: the dynamical system generated by a graph and a vector of rate constants, parameters K, is, as we saw last time, dx over dt is equal this right-hand side. Is exactly what we saw. This is what we will call from now on that we say that the dynamical system is generated by a graph and a vector of k's. Good. Now, another point of view. So if you start with a system that has some right-hand side in a vectorial notation, small f, now we say that such a system has a realization using an E-graph, G, if there exists a vector of rate constants, such that you see this is the left-hand side from before, so the system generated by G and K is the right-hand side of our system. So we are interested very much in finding realizations of dynamical systems. Start with some dynamical system in the ODE expression, and we are very much interested in finding a graph that realizes it together with these decorations that are the case we have. Okay, and now this was very important. For the next slide, I recall that we saw last week the notion of inflow at a vertex and the outflow at a vertex. We saw that you gather, so for the inflow, you add all the quantities that come via reactions towards your vertex. So you have the vertex y0, so you take all the edges y towards y0, and actually the rate constants associated with multiplied by the monomial starting with from the source of that reaction. And similarly, the outflow is just what we saw last time. I recall here to make coherent the presentation, because I want to recall what I said, what is a complex balanced, when does a couple, a graph and the vector K satisfy the complex balance condition. Last week we were saying mostly the network. The network satisfies. Network and graph are the same for us. So we said the complex balance condition is satisfied by the graph and the vector K whenever we have this Kirchhoff balancing in each vertex of the network. So whatever goes, so the inflow is balanced out by the outflow. It's this is not nothing new. For every complex or vertex, if you want to call it, we have this equality. And now to remember, when we have such an x0, a steady state that satisfies such complex balancing condition, we say that the system is toric. Okay, it's a toric dynamical system. Or we also say that it's a complex balance dynamical system. X0 then is a complex balance steady state. Now a new notion appears, and it's not much different. It's not very difficult to introduce. So think precisely as we thought about the complex balancing condition, but now it's a we consider a graph that is called reversible in the sense that we have every reaction has also its reverse reaction. So if you if you have any two vertices that are connected by an edge, a directed edge, by definition, if the graph is reversible, you also have the reverse edge connected. And now we say that such a graph, and we decorated with its parameters, satisfies the detailed balance condition if we have now a different balancing, namely by couple of reactions. So we don't no longer have a balancing in a vertex, but in every vertex, but by pairs of reactions. So whatever goes coming from one direction must be balanced out by what happens on the other, by the quantity that flows on the other, on the reverse direction. So it's very nice. And again, like previously, we said that if such a state exists, then it's called the detailed balanced steady state of the system. And why I introduced this new definition? It is known that, and one can prove, maybe during the tutorial we can prove this, that if steady state is detailed balance, it is also complex balance. So detailed balance implies complex balance, and we will need this in the next in the work that follows. So we have the notion of complex balance, we have the notion of detailed balance. These are the interesting, the key notions here. And finally, I can explain what is a disguised toric dynamical system. So we define together with Laura Brustenga Moncuzi and Gheorghe Crăciun, we say that so given a system, again in the vectorial form, this one, we say that it is disguised toric dynamical system if we find a graph and we find together with the reaction rates decorating the edges, okay, such that the system is has a realization by this graph, and what is the key point is that the couple GK, so the graph we found, satisfies the complex balance condition. Briefly said, a system is disguised toric if you find the graph that realizes it and and that you know it's toric. So you don't see directly, but you see it in using a new graph. A new graph that gives the same right-hand side as you see here. So this graph gives exactly your right-hand side. And moreover, the couple GK satisfies the complex balance condition. This is why we call it disguised, because we didn't know, but if we can find G, we know. And another way of saying it that I might sometimes use is that the system has a complex balance realization using the new graph G. So it has a complex balance realization. Similarly, for detailed balance, we say that the system has a detailed balance realization if we find the graph and together with the reaction rates K, positive real numbers, such that this GK, the couple GK, realizes our system, and moreover, GK satisfies the detailed balance condition, so that balancing on each pair of reversible reactions. So here we could also talk, if we want, about disguised detailed balanced systems. We didn't introduce that notation anymore. So it's just the same, just that now we talk about the detailed balance condition. Now the notation for toric locus and disguised toric locus, because we need this. Now, given a graph G, we denote in this lecture by capital K of G the toric locus of G. So here maybe this will really clarify. So the toric locus is what we saw last week. These are the K's, the parameters that such that the system generated precisely by our graph, the pair GK, is toric. Here really you only think about our graph G, exactly what we were seeing last week. But the disguised toric locus here, K hat of G, are those parameters in the positive order, such that the system generated by G and K is disguised toric. So in other words, exactly what we saw in the previous slide. Maybe there's another here still, maybe there's a G hat, or okay, another graph that satisfies the complex balance condition and gives you, and together with the case, that realizes this system. So here, keep in mind, we say K hat of G, and we find it using some other graphs. Of course, that now the toric locus is included in the disguised toric locus via a realization precisely by the graph that gives a. So I mean, for the toric locus, we know already that it has a realization precisely by G, by the graph we start with. Okay. So we finished with the notations. We are ready to go into the results part and examples.
Hello? Oh, excuse
I
me.
recall, yes.
I just wanted to ask, can you go back to the previous slide with the K hat? So when you defined the disguised toric locus, it seemed like it was associated to a system, right? But now you're taking it of a graph. So I'm just a little confused about how you're getting the disguised toric locus of a graph.
Yes, so it's an interesting question indeed. We decided to think of the graph because yes, maybe we could have thought of not writing of G. That's what makes you ask this question, right? The fact that we
no, maybe
have
even
this
something
notation.
simpler than that. I mean, I'm just confused about the definition, because so disguised toric locus is the toric locus of the graph that is the realization of the system, or sorry, when the system is realized by a graph, then we take the toric locus of this graph. Is that what the disguised toric locus is? Miruna, can you give an example? Can you give an example
Yes.
to clarify what is K and K cap G?
Yes. Let's go to an example, and then we can. Thank you for the suggestion. Here, I don't know what. So I have an issue. Okay, I'll go to this example. Okay, I think it's a good. And then I'll come back to it. But for the example, I actually need one more definition. But just I'll come back. This I mentioned already the dynamical equivalence to understand this definition first, and then because exactly actually you know already what is we say that two reaction networks or two graphs are dynamically equivalent if they generate the same ODE system. So yes, in the example it will be more clear. The right hand side will be the same of the ODE system, but coming from different graphs. And yes, last time I said a bit about this example here. For this graph, we have deficiency 1 if you compute it. And you see at some point you can encounter, using the rule, the recipe for getting the system such a vector times the monomial and the rate constant. And now we would like to see if we can rewrite this. And we rewrite in terms of, we decompose actually in here in green was this green arrow, K1, you see. We decompose it in, we take two components that give that K1 in orange. And it gives here the same, but only if we also accordingly change the rates. So we need to, so we may write this as a sum of two vectors, but keep in mind that when you adjust this, the rates change. You need to adjust accordingly to the length of the new vectors and so on. But now the same system is generated by the orange network. And the orange network has the efficiency 0, which means that all the rate constants, all the parameters, give rise to a nice complex balance. And now we'll go to the example. Let's see. Yes, I think we'll come back to the question after the example. Maybe then it will be more clear. So what we are looking at today, some examples where the disguised toric locus is larger than the toric locus. In the first network that I present in the left-hand side, again, the triangle on a line, we will have an interesting fact. We will prove that even if the toric locus was a dimension 1 semi-algebraic set, we have that the disguised toric locus is the whole parameter space. So we will end up seeing that no matter how you choose the rate constants on the edges, you end up having nice dynamics of your system. The same it will happen for the second reaction. This is what we call the quadrilateral on a line, 4 vertices and complete directed graph. Here it's codimension 2, but we will see again a positive Lebesgue measure 0 disguised toric locus. So the codimension 2 toric locus and positive Lebesgue measure 0 disguised toric. And even more interesting, what we will see today is that we might even encounter such a reaction like the orange one here, where the toric locus is empty, but the disguised toric locus is again a positive Lebesgue measure set. Why is it empty? Because maybe you remember from last time, a necessary condition for complex balancing is to be weakly reversible. So every, I said, every directed edge has to be part of a directed cycle. And here you see that no such thing happens. And actually you can also see directly because there are vertices where we only have inflow. So there's no outflow, and so there are some vertices where there is just outflow. We cannot have the complex balancing on this network. So the toric locus is empty, but the disguised toric, if you play now with the vectors and decompose them and recreate the same system with the new graph that is weakly reversible, you get a bigger set for the disguised toric locus. So now the first example, the first network we are going to look at, this triangle on a line. Of course, we already know the toric locus for it. We have seen it. This is our network, the graph, the deficiency we know it is 1. And now what we proved, we proved that together with Brustenga and Crăciun, we proved that the disguised toric locus of the complete graph on 3 nodes is the whole space. So from codimension 1 toric to the whole space, the positive orthant of, here there are 6 KIJs, 6 parameters, so R6 positive. This is the disguised toric locus. So how do we do this? Now we can think of this in terms of, again, of graph. So first graph is our network. What we can do, and that's the general idea, to find the different graph, sometimes simpler, but in another example, we see also that sometimes we complicate the graph. But in this case, first we simplify it. How can do this? We reduce it to have only one reaction per source. So if you think that we have the reaction y1, y2, and y1, y3, you see they are in the same direction, we can gather them in a single reaction. Here, or let's say, yes, single vector. So for each source, we have 3 sources. For each source, we sum up all the vectors that start on that source, and with our usual expression of the quantities here, Kij times the target minus source. This is algebraically. Geometrically, here is the graph with the new expressions. One reaction per source. What we notice? So we notice that if we do this, if we group the vectors, the first one, so u1 we call it, so the vector in this example, second picture, y1, y3, okay, this is u1, is a multiple of -2, 2. Okay, and it is, let's say, there is this proportional factor k1 star times this vector, -2. And for u3, again, we know that it is a multiple of 1 minus 1. And let's introduce this new rate, this coefficient k3 star. So now, that's why I insisted a bit on the definitions, because we want to realize, so we realize the system generated by the first graph with the rates k by this new cycle-directed graph G star with the same sources. We can do this with this recipe we seen here about with UI. And if you check by construction, really, just by summing up these vectors, the dynamical systems are equal. So we have a dynamical equivalence. And keep in mind here, there are these new rates. These are these Ki, K1 star, K2 star, K3 star. So we want to prove that the disguised toric locus of this new network now is the whole is R3 positive in this case. So what it's a bit that's why I said every example is quite somehow even if the general procedure is or the general idea is the same more or less, we need to adapt to each example because it's about real algebraic geometry now. It's we need inequalities. We need to see how to understand what happens. So in this case, what we do is now we look at the second graph, this new one, since they're dynamically equivalent, and we try to look and work with this, the second one. And what is very interesting is that we will realize the second one. It's really a bit surprising using the first one again. So in the sense that we start with the we start with this. Now we start with this one, and what we do, we consider it. How to say? We create all the edges again from before. So we do another dynamical equivalence with the G hat graph. That G hat is again the complete graph on 3 nodes with some new rate constants, K hat. And I plan that during the tutorial we can look more precisely. We can maybe make these computations if necessary. I don't know. Depends also if it's interesting or not to see better. But what we do another dynamical equivalence in the sense that this G hat has now new rate constants K hat in function of K stars now. And how we do? We add up some parameters. Just we create these so that we get the same ODE system. So they cancel out and actually we get the same ODE system, but this is the new parameterization of our coming from the G hat graph. So now the toric locus of G hat, we knew from Friday that it's this hypersurface. This one here, so it's this given by this equality in the K hats. It's exactly this hidden binomial. And if we pull back this this relation in K hat using this parameterization in number 8, so essentially we replace K hats with the new expressions from 8, we end up with this function phi of ABC. So what we want is that our K hats verify this equation so that G hat is toric. We want to show that there exists such a parameterization, such a new parameterization with having A, B, C as variables here, such that the K hats are on the toric locus of here. So essentially what we do is that we show that there exists indeed A0, B0, C0, such that this phi is 0. So we show that there are A, B, C positive real numbers, such that K hats verify the toric locus of, so are on the equation of the toric locus of G hat. In other words, we show that G hat is toric. And this now, if you think of if you think of what I was defining before, we said that a system is disguised toric if there exists a realization given by a G hat, say, so, such that G hat and K hat satisfies the complex balance condition. So this was the complex balance condition in our case. So showing this, we proved that G star is disguised toric. And in other, since it was for any rates. So in other words, since G star was also dynamically equivalent to G and K, the disguised toric locus is the whole parameter space. So essentially we started with G, we used G star first by taking one reaction per source and found a dynamical equivalence. And then it was not enough. The new G star didn't help us yet. We needed to reconsider another G hat that gave us again a dynamical equivalence. And how we got to the toricity by showing that the new parameters K hat satisfy the toric locus equation, this equation here. So maybe it is quite involved, so maybe the next example may be easier. I don't know. This was a bit complicated because it was using the same, actually, we showed that we use the same graph in the end, but with an intermediate step, this one reaction per source graph. Okay, so this was an example where K hat is the whole parameter space, and it was a good improvement from the hypersurface from the toric locus. If we consider now quadrilateral on a line, 4 vertices, the complete directed edge. Actually, at the end, we will also look at an n-gon on a line. Now we have the triangle on a line, the quadrilateral on a line now. What can we say about this one? So codimension, or let's say the efficiency of this network, if you compute, so you have 4 vertices, we have one dimensional stoichiometric subspace, and one linkage class, one connected component, in other words. So 4 minus 1 minus 1 gives us 2. So the efficiency is 2. That means, by the theory of Crăciun, Wittgenstein, Schiu, and Sturmfeld, that the codimension of the toric locus is 2. Now we will find a positive Lebesgue measure set of this guy's toric locus. How to do this? We always have to see how can we find new graphs that generate the same ODE system. I also didn't mention there is a theorem saying that by Crăciun, Jean, and you, saying that it is enough to check only on the source vertices. So if you add new vertices, it won't help. So that's why we usually search for new graphs on the source vertices of our initial graph. So in this case, what we did to find the disguised toric locus. So we started with this complete graph on 4 vertices. But then we said, let us try to create, again, like in the triangle case, one reaction per source. So again, we added all the reactions coming from, so having y1 as a source, so y1, y2, y1, y3, and y1, y4, we gathered them all. And this can be seen here in the sense that we adjusted we took this minus 1, 1 vector multiplied by its rates from before, but to keep track of the length, we had to adjust the kij's here. So that's what we did. We just grouped them according to their source. First, this is the first step, just grouping them according to their source. But then, since we obtained just 4 vectors, this one, minus 1, 1, 1, minus 1, well, because okay, for the first one and the last one, we know exactly their direction. Y4, we knew that it has, it will point out towards Y1. You can see because Y4, Y3 plus Y4, Y2 plus Y4, Y1, it will, the resultant will be, the result of this, the sum of this will be something that is directly, positively proportional to 1 minus 1 here. This is the one. Similarly, for the vector that has the source y1, it will go, we know precise, so that's why I colored them differently in blue. We don't have there any choice to make for the sign of the coefficients. And then algebraically, you can see this. This is just, you can see this algebraically, because this was a sum, the coefficient in front of it is a sum of positive rate constants. So for the first and the last parentheses here, we don't have any choice. Whereas for the second and third case, it might depend on the values of initial rate constants, which is the sign of this vector, I mean, of these parentheses, and then the direction of the red vectors. So once we start this discussion, of one reaction per vertex, we end up having two cases. for K2 star and K3 star. We denote this by K star, each of them. So in the end, there are 2 by 2, 4 situations that we can see all of them in this picture. So the whole situation for this network, this is all that can happen now. Either, so in function of the signs and namely of the direction of these vectors. This, if you look at the first one in the left-hand side, you see that they go up, 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 and then down. There is one, we call it one sign change network, single sign change network, this one. If you look at the second case, you go up, then you change the sign again, go down, but all the others go down. So you only change sign once. So here is where the real algebraic geometry really comes in a lot into play. In the third, so the left bottom picture, you change sign again only once, but the difference comes in the last one. In the last one, it happens 3 times. Okay, so we will separate now in our discussion the first 3. These are the single sign change chambers, we call them. So the parameters K star where this happens, so that's only one sign change. And the fourth chamber, call it, is separate. And the dynamics will depend on this. So for this network, we completely characterize the dynamics with this theorem. I just wrote it a bit briefly here, and I didn't write the whole, but the idea now is that for the 4 nodes graph, the quadrilateral line, we know that this graph is disguised storic if and only if there are 2 cases. Either the parameters belong to these single sign change chambers, so they verify these 3 cases, or if the parameters K star, this K, okay, initially they were called K without star. If they are on the 4th chamber, so just given by the inequalities there, I said, we also need to impose this inequality in order to be disguised storic. And this completely characterized the dynamics and the disguise. We found the whole disguised storic locus with this theorem. During the tutorial, I plan to prove this together. Look at how we used, essentially here we used the Descartes rule of signs, and we used the discriminant of a cubic polynomial, and we showed it is not very, it is interesting, I would say. Not very long, we can do it. So why I did here these pictures. For now, let's ignore the gray surface in this picture, and we think only of the second case here. The beige surface is given by this equality here. So once we fix K for star, for instance, to be 1 to work in, think of it finely, it's this, it's actually, we can think of it as the Segre variety. So what we showed in this number 2, so how we can translate it geometrically is that all the points in the positive orthant, this is the parameter space here, the positive orthant that we drew, all the points above this beige surface and on the beige surface together give rise to complex balancing or to disguised storic systems. There was a PhD thesis by Anne Shiu, her PhD thesis, where she showed that the toric locus is this Segre variety, is lying on, it's exactly the Segre variety, but now and you see this is a hypersurface, so the bag measure is 0. But for us now, coming from this example, it is the disguised toric locus is comprised of all the points above it and on top of the bag surface, so positive Lebesgue measure. So this is an improvement for the parameters that now we are sure that give rise to nice dynamics. Later we'll see what this gray surface is. I don't know if I explain the proof, or maybe I skip the proof and during the tutorial you can read all the details of this proof in the paper by Vrustenga, Crăciun, Sorea, Disguised Toric Dynamical Systems. And I think it's interesting to look at it during the tutorial and to discuss it together and make the computations. Okay. Now, in the beginning, I was asking this question. If now we improved and enlarged the set with the disguised toric locus, do we cover all the globally stable systems? Because I was having these inclusions that we knew that there are globally stable systems that are not toric. And the question is if now with the disguised toric, we end up having all the globally stable systems. Finally, I can give the answer to this question. It turns out that no, we have a strict inclusion. Here, just a small parenthesis, think about the cases where the global attractor conjecture is proven. We work here in this example, we know it's true. So for those who might wonder, I close the parenthesis. So it turns out that the gray surface here is the surface such that above it there is precisely one equilibrium for your systems. So all the points in the parameter space that are above the gray surface here in the positive order give rise to a unique equilibrium point that is globally stable. But we saw a few slides ago that actually all the points above the beige surface, only the points above the beige surface above it give rise to disguised toric for this network. So it turns out that all the points that are above the gray and below the beige surface, I mean in between, let's say, are globally stable but not disguised toric. And we will see the computations, we can see them in the tutorial. It's nice, it's usually using, actually this is coming from a discriminant. That's why I introduced in the first lecture the discriminant of a polynomial. And this will help us, since these are real polynomials, so we can conclude what I'm saying here. Okay.
Okay.
So yes?
Are we going to stop now?
Okay, we can stop, yes, for questions.
Yeah. In fact, we are at on time now for the next speaker online. But firstly, okay, this is the best time to stop. So
okay, yes, I saw.
Are there any